before handing over to Chris to introduce Seamus, I'm just going to mention next week's seminar, which will be on Tuesday at 5 p.m. And we're going to have a panel discussion on AI, environment and energy. How worried should we be? So I'm hoping that's going to be quite a lively session, and you're all very welcome to that. But now I'll hand over to Chris, who's going to tell us about our speaker today.
Okay, well, a little bit breathless because at one point Seamus's train was greatly delayed, and then he caught an earlier one, so caught up again. So Seamus sent me a long thing to introduce him, but I won't go through all of it because it would take time away from you. So I made a shorter version, but it's still quite long, so we'll give you injury time if it's too long, because it's quite interesting. So Seamus is Professor of Mechanical Engineering in Nottingham. His original specialization was machine vibration, initially focused on large electrical machines and subsequently on the dynamics of gas turbine engines. For 12 years, he was director of a Rolls-Royce supported University Technology Center in gas turbine transmission systems. But in 2005, he recognized that research in clean energy would be a rich vein of opportunity for mechanical engineers. And it occurred to him that storing pressurized air in fabrics held deep underwater could be economically practical. This fall, he failed to interest his colleagues in this thought, right? Although calculations suggested that it could really make sense. And as a consequence, anyway, he became increasingly interested in energy storage and its integration with renewables. And this integration of storage and renewables is now the main focus of his talk. Seamus is particularly interested in the role of medium duration energy storage in energy systems, which isn't a very well-defined term, unfortunately. And he's organized numerous one-day events on this topic, 4 addressing hydrogen storage in caverns, and other one-day events on energy storage policy and on grid inertia, which most medium duration energy storages provide. He's currently leading a task within the IEA Technology Collaboration Program on energy storage that focuses specifically on medium duration energy storage, and is one of the co-founders of Cheesecake Energy Limited, which employs 30 people and is developing this technology of modular energy storage units based on storing both pressurized air and heat. Seamus organized and chaired the UK Energy Storage Conference last year, and he co-founded the Off-Seas Energy Storage International Conference series, which have taken place all over Europe, I think, or maybe the world. He played a very important role in the Royal Society's study of large-scale electricity storage, which I led, which was published in 2022. I gave a talk about it in the autumn of 2022 and got into a lot of trouble by saying that the government had got it wrong. They have got it wrong, but they didn't like hearing that, or at least the people who told them the things that were wrong didn't like it. His particular contribution was to show that in blending in some medium duration energy storage to complement hydrogen storage, which you definitely need, could lead to some useful overall cost reductions in the order of 5 or 12, 10%. As you'll see, whether it does is very critically dependent on cost. He and I are continuing to work together, attempting to ensure the main message of the Royal Society report are both understood and acted upon by His Majesty's government. It's hard to say that at my age. But I had a meeting with DESNZ last week. They're beginning to get it, and he and I have another meeting with people in DESNZ at the end of the month. So that's more than enough over to you.
Thank you very much indeed, Chris, and thank you to everyone in the room for giving me some of your time. Whenever anybody invites me to give a talk, the answer is immediately yes, and then after that, how long have I got? And I'll attempt to stay within about 40 minutes from start to finish here. I'm a man of many flaws, and Chris has pointed out, alluded indirectly to some of them, but particularly I cannot let stuff go. So if it's wrong, I can let it go. And if it's right, I'm unfortunately infected with the imperative to carry on and do something about that. And that's a very unhealthy state of being that I don't recommend to anyone, but I will tell you some of my ailment in that respect. within this talk. So how do I page here? So I'm going to start off with the very few things that Chris and I definitely agree on. And then we're going to go into where we possibly diverge, but possibly not. We haven't discussed that much. The very, in scientific terms, very simple stuff is summarized in pretty much this slide from the Royal Society report. And it basically says that a net zero use is achievable and affordable. And that if you wanted to do that in the best way, you would mostly, if not entirely, generate the electricity from renewables. You would mix wind and solar by energy in approximately an 80-20 mix by energy in order that you balance out seasonal imbalances. You would create a lot of storage capacity in the form of hydrogen stored in caverns, which has been quite a revelation to see how practical that is. And you would have an enormous amount of storage capacity, about 50 in broad brush terms, and these are very broad brush, the equivalent of 50 days consumption of electricity. As it happens, in 2011, I attended a seminar called Pragmatic Approaches to Energy Storage at the IEE, as it was then called, in Savoy Place. And I gave a presentation based on 10 years of data. And I said pretty much that I think we could get by with 6 terawatt hours of storage. And there was a guffaw around the room at such a preposterous number as 6 terawatt hours. And now we have got a doubly preposterous number, but it's a real number and it doesn't cost the earth. The storage input power has to be in the order of mean generation power because we're going to have very variable renewables, and the storage output power has to be in the order of peak power consumption, because sometimes you will have very little renewables and you'll need to supply somehow. And these numbers down here are a section from a summary chart that I did elsewhere. But the key point is that the bottom line represents the cost of everything, the whole system, measured out per megawatt hour. And the top line is the primary cost of generating the renewables. And the biggest cost of all in the future will be the primary cost of generation. So the ability to add flexibility in is less than that much, but it's significant in very simple terms. So if generation gets more expensive, then obviously wholesale prices, these are wholesale prices of electricity, they become more expensive. And I've plagiarized, in the finest traditions of academic life, 2 graphs directly from the report, because these are very succinct in explaining the relatively simple matter of why do you need so much hydrogen storage. And it's really got to do with inter-year, and Chris would say interdecadal, variability of wind resource. The slides will all be available, by the way, and these are plagiarized directly from the report. So feel free to photograph whatever you like. So the first one is a version of the shortfall or excess year by year if you had scaled up supplies to be suitable for 570 terawatt hours per year of consumption. And the second one shows you the state of fill of the hydrogen store. And this is really insightful because the hydrogen store, first of all, stays full most of the time. And so that's quite an interesting thing, because what that tells you is that a lot of the time you are actually not able to put more energy into it. And therefore turnaround efficiency is less sensitive than you might think. And secondly, this is Chris's own writing, there's a very big gap between the time when you must fill up a store and the time when you must empty it again, potentially, for some of the bulk of that capacity. So that's easy stuff, and that's from the Royal Society report. And if you say, so what? Well, the utterly obvious fact is the UK should already be preparing a large amount of salt cavern storage for hydrogen. It isn't. And it's so incredibly simple to explain that, but it isn't happening. So that's unfortunate. We should be preparing for several gigawatts worth of electrolyzers and hydrogen-fired engines, or some other way to convert hydrogen into electricity, and we're not. Although there are intentions of 5 gigawatts by some target date, I can't remember that. And the above two are not only essential, but they are no regrets. So even if we're not right about many of the aspects of cost and performance, there's almost no probability that these things will be will lead to regret. So we should just be doing them. And with that, I could stop there, and Chris would be happy if I did. You could say that's the answer. In my opinion, that's a part of the answer. The rest of this talk is about how you can make the answer better. And fundamentally, there's no point in making the answer better until you've got that message across first, which is where we're at right now, struggling to get that message across. However, I want to focus mainly on how you can make it even better than that. This graph is what I hope people will recognize in a couple of decades' time as my signature graph. It doesn't have any numbers on the axes, and it's got very strange units. So along the bottom axis is the log base 2 of discharge duration, measured in whatever units you like, seconds, let's say. And the thing to note about energy storage is that the range of discharge durations that are relevant to us is colossal. It's bigger than any other dynamic range that we commonly come across. So it goes from seconds up to a couple of years. And I think it doesn't go beyond a couple of years, because if you think about timescales longer than a couple of years, you could just build more stuff. And if you think about things shorter than seconds, actually things like inertia and spinning rotors automatically sort that out. They're relatively simple things. They're local effects, and you don't have to worry about them. But the ratio between a second and a couple of years, it's about 2 to the power of 26. It's absolutely colossal. And then on the vertical axis, there's a unit that's particularly difficult to explain. I won't attempt to unpack it completely, but it's the cut per semitone. Now, if you're a musical person, you will realize that a semitone is the 12th root of 2 increase in frequency. And because frequency has an inverse relationship to time, you can think about the semitones in time as well being a factor of 2 to the power of 1/12 more. So if we started with 1 second as the lowest discharge duration, we can then go up to 2 to the power of 1/12 seconds and so forth, and et cetera, et cetera. And my key message is that there are 4 main ranges of energy storage. There is the long duration storage, which is over here, which has to be handled by fuels for the very simple reason that the thing that matters is the cost per unit of energy storage capacity. And hydrogen is going to be the king there, potentially ammonia, potentially some other things. The synthetic fuels have another role, potentially biomass has some role in here. And at the very opposite end, this is easier to understand. This range is short duration storage, which I think runs from 10 seconds, maybe 30 seconds, up to a couple of hours. And this is dominated by batteries and always will be, for the simple reason that the cost per unit power associated with batteries is very low compared to anything mechanical. Trust me, an inverter and some batteries is cheap power. So batteries are going to dominate here quite rightly. Fuels are going to dominate up there quite rightly. There is another interesting space down here where what matches is the cost per unit rate of change of power, or power slew rate. And that is actually dollars per megawatt per second. Curiously enough, it's how much do you pay for the ability to change output power very quickly. And things like flywheels and capacitors are going to dominate down there. And in the middle between long and short is a whole set of times where actually you can address these using hydrogen if you want. It's just not a good solution because the cost per unit power is high and the turnaround losses are terrible. And you can address them using batteries, but they're not a good solution because the cost per unit energy storage capacity is too high using batteries. So there's a whole space here, and I want to mainly impress upon you how big that space is and how important it is. So essentially, there are 3 sections in this talk. After that was the preface. The first one is I want to tell you about the distribution of energy that will come out of storage. You can chop it up according to the periods of continuous discharge from storage. That's the first message. The second one, I want to tell you about a tool that I wrote, first of all, to support the Royal Society report, and then thought, well, actually, I could tart it up and make it suitable for people to use independently of me. I wrote it for me to use in the first instance, but then I realized it's not hard to make other people able to use it. And the final one, if I get this far without running out of time and interest, I want to tell you about my passion, which is one of those personality disorder issues, and it is about the idea of integrating energy storage right into wind turbines. And you're guessing what that means, and you're wrong. So let's start with the First one. By the way, I'm going to introduce you to my imaginary friend, Jim, whom I invented last night with ChatGPT. So this is actually a graph that I did present at that event in 2011 at the IET. Well, it's similar to a graph, it's obviously not that one because of the years, but it's 10 years of what I call net demand. And net demand is what you get when you scale up the supply coming from wind and solar power, such that the amount of energy that you've produced from the supply is a bit more than demand, like in this case, 10% more. So I call that 10% overcapacity. And then you subtract demand from that. And what you're left with is net demand. And net demand is sometimes positive and it's sometimes negative. So far, so good. And in this case, because there's overcapacity, it has to be on average negative, because we're generally speaking producing more than we need to draw out. And we assume for the moment that energy storage is 100% efficient. So it just gets us a rough idea about the shape of the problem that we're addressing. And I want to focus on the positive bumps, the positive half cycles, not the negative ones. The positive half cycles are when energy is coming out of storage. That's when it's valuable. The negative half cycles are when you're putting energy into storage. And it's by definition, some people would call it excess. I hate the term, but it's less valuable when it's going in. So the area we ought to focus on is this stuff that's coming out. And you can do a very simple operation on that. You can zoom in on the graph and you can look at every place where net demand is positive. And you can say, right, how long did it stay positive for continuously? And each one of those bumps then can be categorized according to how long did it last. And it's quite remarkable what you then find if you analyze how much of that energy came out in bumps that was shorter than 4 hours, less than 1%. So in other words, the natural duty, so I'm not saying that batteries can't do more than this duty, but I'm saying this, the duty that falls most naturally to batteries appears to be less than 1% of all the energy that comes out of storage in that picture. And then again, look at the other end of the spectrum. How much comes out in periods that are continuously short for more than 200 hours, which is about a week, so 8 days. And it's about 7%. That's quite surprising, but we get this word is now commonly accepted by all of us, Dunkelflaute, a German word. A Dunkelflaute is basically something that's about 8 days long, 4 to 8 days long. It's a period of cold weather and no wind. We had one. Actually, we've just lived through one. And in the middle, all the action is in this medium duration range. So that's a kind of interesting observation. And you can take that a little bit further and you can say, well, instead of dividing it up into 3 bins, I can chop it up into semitones if I want, as I proposed earlier on. And this is it on a linear scale. So this gives you a probability density function, indicating to you for any 1 kilowatt hour that came out of storage, what is the probability that it came out within in a period of continuous discharge of a certain range. And well, perhaps not surprisingly, you find a bump at around 12 hours, and that's because there's quite a bit of solar in this. So you quite likely have a period of solar where you definitely don't need anything coming out of storage. And then you have a period when you do, and then solar kicks in again. So it's not surprising we have that. And I was puzzled initially by these, looked like harmonics of that, but it's actually quite easy to understand. If you ran short of electricity all the way, which way around am I? Yeah. If you ran short of electricity for 24 hours, you'll almost certainly run short for 36, because you'll be through to the next period when the sun isn't shining. So there is actually quite a logical explanation for why these humps turn up. And effectively, that just reinforces the message. You can put the boundaries on here. There's 200 hours and there's 4 hours. Or I much prefer to present it now in a logarithmic scale. So you can think about these as this is the log of discharge time. And that is the probability density per semitone, if you want. In effect, what I've done is I've taken every vertical slice out in here. I've multiplied its magnitude, its height by the average time, and I've divided its width by the average time. And put it on here, just stuck them all up that way. And that turns that into the log, believe it or not. and you get a logarithmic distribution function. I've got friends who deal with reliability and probability, and I asked them what's the name for this graph, and they can't tell me. I think I may have invented a form of probability density function. It's quite easy to understand, and it's sort of interesting again that there's a big lump, a swathe of activity in the middle here where it's all happening. Okay, this one. So that's the end of section 1, and this is my imaginary friend Jim, and I'm putting words into his mouth, and he's saying, so most of the energy supplied by storage in net zero UK will emerge in periods of discharge in this medium duration range. And he quite rightly tells me back that this doesn't mean that you should necessarily supply all of that from medium duration storage. You could do it with hydrogen and batteries. So section 2, well, so how do you go about optimizing a system that has multiple stores in it then? And this is that piece of code that I told you about. I wrote a piece of code, I call it NStore Sim, for a very simple reason, that it's all about simulating a system that has N stores in it, multiple stores in it. And it's open source in not the proper way, but you can copy it and use it. It's written in MATLAB and it's available at that link. And it's a set of MATLAB functions with some example main scripts showing you how to use them, and some explanation videos. And at the core of it all is the idea that you can describe your system using a vector of parameters, which to you is going to say, how much hydrogen storage have I got in terawatt hours? How much electrolyzer capacity have I got? How much engines have I got to convert back out again? And then the same thing for other stores, that forms a vector. And then you can calculate the cost, the minimum cost of the system that will work with that vector if there is one. As long as you pick sensible numbers in here, there will be a way to make that system work. You can calculate the minimum cost. And if you can do that, you can throw it into a dumb optimization tool, which is in MATLAB, and it will crunch for conversation we were having yesterday, day before. It'll crunch for 2 days on a laptop and say, oh, here's the best you can do. So this is what NStore Sim does. You have to, for each type of energy store, you have to tell it these things. What does 1 unit of input power cost? So cost per kilowatt. What does 1 unit of output power cost? What does 1 unit of storage capacity cost? And how efficient is it in round trip? And I don't care what it does inside. If I know these numbers, that to me describes it perfectly well for present purposes. And very importantly, you have to attach a cost to the difference between the state of charge at the end and the state of charge at the beginning. Because if you don't do that, you must constrain yourself to bring it back where it started. And that turns out to be quite an important freedom to have, to not require it to go back where it started. So that's what it broadly, that's the information you need. I'm going to show you how it works with a single energy storage system. You have, for a single energy storage system, you have 4 variables, but only 3 of them are independent. This doesn't, oh, it does, it's very faint. So there are 3 variables that are independent, and then there's 1 that's dependent. You can tell it how big is the storage input power. You can tell it how big is the storage output power, and you can tell it how big is the store itself in volume terms. And then it can calculate, given those 3 things, how much overcapacity you need in order to supply all of the demand. So if you make your stores very small, or low input power, low output power, and low capacity, then you're likely to require a vast amount of overgeneration, and possibly an outlandish amount of overgeneration. But as long as you make reasonable estimates of this, if you start off in a reasonable land, it will find a value of X such that the system works. So far, so good. So if I say I'm going to have 10 terawatt hours of storage, 30 gigawatts of input power, 40 gigawatts of output power, it might well be that some of the 40 gigawatts of output power could even be unnecessary. It doesn't, oblivious to whether it's necessary or not. It will say, in order to make this system work, you have to overgenerate by 25%, 30%, 40%, whatever the number is. And then having determined that value of X, it will calculate the cost. And then what it will do, the NStore sim, is it'll play around with these numbers. What if I made G a bit bigger? What if I made it a bit smaller? What if I made H a bit bigger? Automatically, you don't see any of that. And it says, oh, I'll follow it's a simplex algorithm. I'll follow the simplex down the hill and get to the bottom of the hill. So it does a cost optimization. So the test really, or the fundamental capability here is to test whether any one four tuple, a combination of four numbers, works. And in order to determine whether it works, you initialize the energy with some initial value, typically 70% full we might take. You step through every 1 hour period in a record, which in the case of the analysis done in Royal Society report was 324,000 hours in the period. If supply exceeds demand, you put the excess into storage. It's very simple. If demand exceeds supply, you draw out some to cover the shortfall. And by the way, when you're putting it in, you implement all the inefficiency there. So you have to account for the inefficiency. I chop it off here. You can, in a way, decide whether you're chopping it off at the input or the output. It all depends on how you want to define capacity in terms of how much you can put in or how much you take out. I prefer to define capacity in terms of how much you can take out, because that's electricity. That's what we really value. There's absolutely no purpose here for being able to forecast. Quite interesting. It doesn't make any difference whether you know what the weather is going to be like tomorrow. You've got the energy today. If a big wind comes along tomorrow and you've got too much energy tomorrow, you put it in store. What else would you do with it? And if you're short, you take energy out of store. Where else would you get it? You can't. There's nothing you can do with a single store other than do the best you can.
Seamus, it's one type of store and no other sources.
And no other sources, and no other stores.
Nuclear, no gas plus CCS.
No discretionary sources like that.
We're coming to that.
Yes, indeed. And so Chris basically did the same calculation that I did in a different way. Chris did it as a manual version of this for the single store case. And this is the NStore sim version of the same thing. And actually, these graphs, they look very similar. They've actually got the axes flipped. But it's the NStore sim case enables you to deal with the multi-store case. And Chris essentially asked for, if you know what the input power is and you know what the store capacity is, what does the volume of store have to be in order to make this work? And you can keep on trying with ever smaller or larger volumes, and you'll find eventually there's enough to make it work. So this surface represents the minimum viable system, as it does on the left-hand side. And the extension to 2 or more stores is really quite simple. Instead of one value for input power, now you've got 2. There's G1 and G2. Instead of one value for output power, there are 2. Instead of one storage volume, there are 2. There's still only one overgeneration factor. So these are the independent variables. You can set these, and then NStore sim will calculate what's the minimum value of overgeneration I need. And nearly always it can find some value that'll be sensible. And then it will calculate the cost. And since it can do that, you can go through the process of exploring the space, turn G1 up a bit, turn G2 down a bit, etc. You don't play any part in that. It's just dumb optimization with no other need as it happens. And this is how you test whether a particular 7 tuple, this is a set of 7 numbers in a particular order, works. It's very similar to the case of how you test whether a single store works, but there's a slight difference. So you initialize as before with about each store about 70% full, let's say. You step through every hour of the period as you would have done before. If supply exceeds demand, you put some of the excess into store, but which one? And if demand exceeds supply, you draw energy out of store, but which one? So the difference is you now have a scheduling problem. You have to decide which store you're going to supply preferentially or withdraw from preferentially. And there is a very simple version of that. Use the most efficient stores as much as you can. And that indeed was both Chris's initiative and instinct and mine. And it's not right. It's not right because if you do that, you will take the most efficient store, and if you're short of energy, you'll empty it. And once it's empty, its output power is no longer in the game. You can't use that output power because it can't deliver you any more energy. So it's actually best to try and avoid emptying it, bring it down, of course, but when you get to about 15% of empty, from empty, then try and use a less efficient store so that you keep that output power in play. And that's been formalized into an algorithm because I've more or less explained it. This graph just represents what that algorithm is. I hasten to add, I didn't invent this, but I very much like it. Stan Zachary at Heriot-Watt, formerly at Heriot-Watt, did invent it. These four curves effectively illustrate the way that you preferentially decide, you schedule. Which store should I draw power from? Well, you draw power from the store that has the lowest marginal value. So you think about it as a greedy process. When you want to take energy out of store, you take it out of the store which is going to sacrifice the least value. And that means that initially, which is discharging, here we are discharging. So initially, if you look at the red line represents compressed air energy storage. Well, that's lower than the blue line. So if I want to discharge, most of the time, I like to take energy out of the red line, but there will come a point, oh yes, when I'm taking it out, this red curve climbs up here. And so here, when it gets down to about this empty, all of a sudden it's better to take energy out of hydrogen. It's just a formal way to make sure that you try to stay away from the buffers. It's driving a bumper car around in a rink and trying not to hit the boundary, because if you hit the boundary, the power goes out of play, and you want to keep the power in play. So that works, it's been implemented, and then you can start to think about grand ambitions. How do I optimize a system with n stores in it? And now you've got, well, as many parameters as you want. All that happens is the compute time goes up. It's absolutely no more challenging to do it for 5 stores or 6 stores or 7 stores. For me, it just takes my laptop longer, and it's still a laptop job. You can still do this all very simply. It's the same routine that you had before. You initialize each store with about 70% of fill, step through each 1 hour period in the record, and then these two, well, if supply exceeds demand, then you do your scheduling. You say, which store do I put this into? And if it's the other way around, you say, which store do I take it out of? And you march your way through time. So you wrap all this together, and it actually turns out to be very revealing. And here's a few conclusions from looking at that. So I haven't presented all the numbers. I've just picked out some conclusions. The first one, the blend of wind and solar matters a lot. And there's a huge amount of misunderstanding with people using the word seasonal. The problem is not winter versus summer. This is greatly misunderstood. People think we need more energy in the winter. That's true. That is not the driver for big energy storage because the wind blows more in winter. So if we blend wind and solar properly, we already have approximately a year-round balance. The big issue is the inter-year issue. So if you get the right blend here, 80-20, to make the seasons right, that's good in terms of not having a seasonal imbalance, but you're actually potentially pumping up the level of wind, and you're pumping up the level of interannual variability. So in actual fact, your best bet intuitively is to start by balancing the seasons first, and then back off a little bit on the wind. So you get a bit less year-to-year variability. That's the first interesting conclusion, I think. You can examine whether nuclear power has a role, and Chris and I have come to a form of words that explains the conclusion here. It is almost a theorem. I thought initially that I could prove that if you postulated a system that ran only on renewables, and you calculated that that could deliver power at 65 pounds per megawatt hour, let's say, then I thought it was a theorem that if nuclear power cannot do that, it has no place. And it turns out that there are you can contrive exceptions to that. It's a very good benchmark, but it's not a theorem. It gives you a very, very good benchmark. And so when people talk about baseload power, which I despise, by the way, absolutely despise the term baseload because it sounds motherhood and apple pie. It sounds such a good thing. It's not a good thing. It's a bad thing. It's inflexible. But when people talk about it in glowing terms, nuclear power is effectively baseload power. If you want to spend a certain amount of money, you should compare it with the cost of the system without any of that baseload, and you can apply the almost a theorem logic to say, should you have any of it? And the third one here is if you put in more nuclear, you chop off the bottom end of demand, and you exacerbate, therefore, the difference between winter demand and solar demand in what's left. And so you want more wind then. And then, interestingly, kind of corollary, you then are a little bit more exposed to variability between the years. And there comes a point where you don't want any solar if you're trying to balance. If you put in nuclear, then you've pushed up the bottom end of you've chopped off the bottom end of demand. Then your variability between winter and summer of what's left is very big, and you want to do it all with wind. So that's also quite interesting. This one is particularly charming. You can treat gas-fired generation as an energy store. All you have to do is to say, unlike other energy stores, you can never refill it. So it starts with an enormous quantity. It ends up with less than that. You must pay for the deficit between input and output at a certain number of pounds per megawatt hour. But otherwise, it behaves in every respect as an energy store. And so you can just throw it into this machine, and out comes the answer. And bizarrely, under very reasonable assumptions, the optimal amount of gas that we should have in the UK is 0, which is rather at odds with the strategy for Clean Power 30 at the moment. And under realistic assumptions about compressed air energy storage, you could be having reductions in whole system cost in the order of 5% relative to a hydrogen plus batteries only system. In other words, a system where you did all the flexibility using only batteries. So this is a graph that's again plagiarized directly from the Royal Society report. And the graph actually brings out a massive issue about some of the medium duration energy storage technologies. And the massive issue is uncertainty. We both tried very hard to find a simple answer to a simple question. How much is a compressor? How much is a 250 megawatt compressor? That shouldn't be hard to answer. It turns out that is hard to answer. We got the answer for electrolyzers within a factor of 3, and the answer for compressors has a factor of 10 associated with it. We couldn't be very confident it won't get cheaper than £60 per kilowatt, and very confident it won't be more than £600 per kilowatt. But there's a very wide spread, and the reason for that really is because at the moment they're made as bespoke items. There's no industry for making 250 megawatt compressors as a standard object. And there's less uncertainty around the efficiency that you'll achieve with this. With compressed air, you certainly be in the high 60s. And so you can read off this chart. If the power was this much and the efficiency was that much, you can read off numbers. And 8% is very credible as a reduction relative to the baseline case, which is already a sort of essential thing to do. This on the right-hand side is a table, it's a piece of output that comes directly out of NSTOR Sim, and it tells you about the breakdown of costs, basically, in the optimized system. And this was optimized with a 2-store system. It had some compressed air in it and some hydrogen in it. And I want to pick out a few key observations in here. So the first observation is that with this optimum combination of compressed air and hydrogen, most of the energy comes out of the compressed air energy storage system. It doesn't come out of the hydrogen. And that number is here. 2,022 terawatt hours comes out of compressed air, and 1,400 comes out of hydrogen. And that's completely consistent with what you should intuitively expect. You don't want to put energy through the form of hydrogen because you lose a lot of it. Perfectly sensible. So that's kind of interesting. you cut down the overgeneration factor. I didn't show the counterfactual case, but the overgeneration factor in the baseline case was 30%. And in crude terms, it is saying you need to generate 30% more electricity than you will consume. A half of that will be thrown away in losses in storage, and a half of it will just be thrown away because that makes the cheapest solution. This was particularly interesting to me. The spend, even though the medium duration energy storage is a much smaller store than the hydrogen. So here we had 5 terawatt hours versus 50 terawatt hours. The spend on the medium duration is about the same. Well, it's slightly less, but it's about the same. So it's not like a sideshow. And this, for part 3, this is really important. About 15% of all the energy that gets consumed has come out of storage. And that means that about 25% of all the energy generated went into storage. And that's a very key point because a lot of that energy came from wind power. And it sets me up very nicely for the final bit. So here's Jim again. And this is Jim's observation. The cost optimization outcomes do seem to suggest that there could be a good role for MDES. But it's a pity about a high degree of uncertainty on costs and performance, costs particularly. And actually, I'm not sure if I've written a conclusion specifically about that. I do think that that may be the biggest single area where more research is needed, because how do you determine how much a 250 megawatt compressor would cost if you were to be building 10 gigawatts of them? There's no established procedure by which at the moment you can determine that. And I think if we knew the truth, it should be very influential on what we do. Right, so this is the final little bit, and I'm indulging myself here. I might curtail myself before the end, to use the analogy. There's a few different, this is about wind integrated storage and some other varieties of medium duration storage. So I've mentioned medium duration storage. And there are quite a few technologies that could slot into that, most of which will be familiar to you. Flow batteries, everyone's heard of. It's 2 tanks of electrolytes that you flow in and flow back out again. And the more tanks you have, or the bigger the tanks, the more capacity you can make. So you can separate the energy storage capacity from the power. That's a good thing. But they tend to be suitable for the bottom end, I would say, of medium duration energy storage. Still a relatively high cost per unit energy. So more focused down towards the bottom end. And then all the rest of these are mechanical things, which is pointed out at the side. Pumped hydro, everyone knows. We've got a plant proposed in Scotland called Curry Glass that's been talked about for yonks. And pumped hydro is very, very mature. It's very good technology. It will last for centuries. Which is a critical issue. I mean, all of these technologies will last a long time by comparison with electrolyzers and batteries, I would say, probably. All of them will last a long time, but pumped hydro, you're talking the civil constructions will last for centuries. So there's an interesting conundrum about how do you finance those things that are going to last for centuries. They're limited by geography, as you very well know. Compressed air energy storage. There are many varieties of these. It's very irritating when you hear or read a report that talks about compressed air energy storage as though it was one thing. There are as many different varieties of compressed air energy storage as there are battery solutions, and that's many. But the UK is fantastically fortunate to have very good resources of bedded salt. We're massively rich. We talk about how rich we are in wind, rightly, but this is not even secondary, I would say. We're very, very fortunate to have a lot of resource in bedded salt. There's liquid air energy storage is out there, which is a UK initiative primarily. It wasn't invented in the UK, by the way. It was invented a long time ago, but the particular variant that's gone forward with Highview is being spearheaded in the UK. There's pumped thermal energy storage, which is effectively using a reversible heat engine heat pump. So a heat pump is like your fridge. You suck heat from a cold, push it up to a hot place, and then a heat engine does the opposite of that. It allows heat to go back from the hot thing to the cold thing, and it's analogous to pushing water up a hill and allowing it to come back down again. When the water comes back down, you can fetch some of the work back out. And then I won't expand on this very much at all, but there's a thing called CO2 batteries that involves liquefying CO2. So CO2 is a remarkable fluid because it will turn into a liquid at relatively modest temperatures. I think it's -30 or something like that. It's very easy to maintain CO2 as a liquid. And so you can cycle it between liquid and gaseous states. The challenge is, what do you do with it in the gaseous state? You have to arrange a huge tent around this great big balloon of CO2. And I think that's a huge challenge with it. But it's out there, and there's an Italian company trying to push it forward. This is the core of what I really want to talk about. We are going to get a massive fraction of our future energy from wind. And at the moment, this is the thought process that we have. We take in mechanical power, by the way, from a wind turbine. It's mechanical energy that comes in from the wind turbine rotor. We might or might not have a gearbox. There will be a generator. There will be a converter. And that's electricity here on this line. And then we will use some of it. In fact, 80% or 75% of it, at least, will be used directly. Great. So it's about what do you do with the rest of it. Do you take 25% of all the energy that you've generated and convert it into something to store it, and then convert it back again to bring it out of store, at which point it's turned into 15% of the consumption? Because if you do that, there are some losses. You're looking dubious there, Nick.
The batteries can be a bit higher efficiency than that.
Oh, I'm being quite generic. You're quite right. Batteries, of course. Yes, you're quite right. Depends on what energy store you use. You couldn't afford, I mean, it would be eye-watering to do terawatt hours of batteries. So yeah, yes. So if you did that, and that's the mind pattern that we're embracing at the moment, 25% of all the energy is collected and transformed from mechanical to electrical, primarily. That's what wind turbine does. And then we'll transform it back into something, maybe not mechanical, but quite likely mechanical because of the durations involved. Wind power particularly does not switch on and switch off in 4 hours. Wind power stays on for a few days at a time and goes off for a few days at a time. It has time constants in that order. It's not short term, and it's not 200 hours that it stays on for either. So, bizarrely, the current thought process is we'll collect this mechanical energy, we'll turn it into electrical, we'll turn it back into mechanical when we put it through storage, and then we'll turn it back into electrical again. And okay, you can do that, that's possible, but maybe there's a better way. And I think there is a possible better way, which is wind integrated storage, where you gather the power mechanically. You might put some of it into a store in the form that's either mechanical or not far away from mechanical, by which I mean thermal. So X is either mechanical or thermal, and then you might combine them back together again. And in that case, you do two key things. You transform the energy fewer times, and you have fewer pieces of power conversion equipment. So there's an efficiency gain, and there's a capex gain, potentially. And this improved utilization of transmission lines, if you can make an offshore wind farm be more steady in its power output, then you can get the same energy through smaller transmission lines. That's also quite a useful thing. So I've been interested in this since 2011, I think. And I wrote a paper back in 2015. And in that paper, I inaugurated this idea of throughput efficiency. So that includes what went through storage and came out again. It's not just what was generated. It's you take the ratio between what was consumed and what was generated. And some loss occurred in storage. And so this graph says, how, on the horizontal axis, how much of the energy did you put through storage? And on the vertical axis says, what fraction did you get of the input did you get to consume? And if you put almost nothing through storage, then you should use a conventional wind turbine for sure, because it's very efficient, about 96% conversion rate between the mechanical power in the rotor and electricity. Fantastic. Conventional wind turbine, absolutely brilliant. But if you're going to put something like 40 or 50 or 60% through storage, you are actually much better off to use an integrated system, because it starts out being less efficient, but its storage losses are basically very, very much smaller. And so you win. And you might say, well, didn't I say that 25%, only 25% is going through storage, which is here, which is sort of borderline. So, which is a very good point. But you shouldn't use this integrated storage for all wind turbines. You should use it for a small fraction of the wind turbines, like a third of them. And then for those wind turbines, the amount of energy that goes through storage is up here. And then you're much better off to have had that type. And I'm going to speed up towards the end. This is an animation. I'm going to explain what happens and then run it. On the horizontal axis is an over-generation factor. And on the vertical axis is fill levels for the different energy stores that are available. In this case, there are 3 energy stores available. At the moment, the over-generation factor is just 100%, so it's no over-generation. And you see that the stores are almost empty all the time. And what that's telling you is you're failing to meet demand, because the stores are trying to empty all the time, and unless those stores go above this line all of the time, you've not met demand. So this is the amount of unmet demand on this vertical axis, and that's the distribution of fill levels of the stores. Here's the animation. And so as you have more and more over-generation, these things tend to lift off the bottom axis. The thing that's going up and down most frequently is the green one, which is a wind integrated storage case. The next most frequently used is the red one. And just at this point, all of the fill levels have now managed to stay above 0. And now you have met demand for the first time, and that was with 19% over-generation factor. And so it's an illustration of, it's really an illustration of N-store sim working. So I think I'm going to skip a few things and jump pretty much straight to the conclusions. There are several different ways that you could do this wind integrated storage. This slide and the next slide enumerate those, and I'm not going to tell you about them because there's one clear winner, there's one clear best, and it's my solution. And that one is called Wind TP, and it's thermal pumping built in directly into wind turbines. And that's an example of a paper from 2015 that describes this thing. Effectively, it builds 2 things into one system. So here's an explanation of how it works. This is the turbine, this is a wind turbine rotor. This is how hydraulic transmission works, which is a good preface to wind TP. So if you wanted a hydraulic transmission, you would take a wind turbine rotor, you would drive a huge machine that's a very slow hydraulic pump. It would send hydraulic fluid around in a loop. And at the other end of that loop, you'd have a hydraulic motor that would take out the power from that and turn a generator. And this thing will turn 50 times or maybe 100 times faster than that. So if you think about all this, this is like a hydraulic gearbox. And these have been built and they worked great. They were absolutely fantastic. Artemis built one. They just didn't have enough argument relative to an electrical drive, direct drive. And this is wind TP. So it looks a bit more complicated, but it's the same basic idea. Instead of a pump, we have a compressor. So now it compresses a gas instead of just pumping out liquid. And instead of a hydraulic motor, we have an expander. So now it expands a gas instead of just taking energy out of a liquid. And the wonderful thing about compressing a gas or expanding a gas is that it changes temperature. So these operations are adiabatic. That compresses, and the temperatures here could get up to 800 Kelvin. 800 Kelvin, and you can take heat out. And when you expand, if the gas coming in was about 350 Kelvin, a bit warmer than ambient, you will go down to 100 Kelvin and you can take the coldness out. So that's just the very edge of something. I'm going to show you a few pictures and then shut up. So all of that is details. Oops. Here are some images. This is an image of the wind TP compressor. And it's a very strange machine. In all probability, it's the most expensive compressor per kilowatt that's ever been built. It's also, I'm hoping, I was hoping already today, it would be the most efficient wind compressor ever built. And I do believe that in a couple of weeks' time, I hope to confirm to you all that I have won a Guinness Book of Records entry for the most efficient compressor ever built. It has to be the most efficient compressor ever built because of a very strange duty. It needs to have relatively low losses. The idea of it's very simple. There's a shaft here that you turn. That causes oil to be pushed forward and backwards inside these cylinders. That causes oil to rise up and down inside what I call organ pipes up there. And that in turn produces a liquid piston compressor. And I could talk for hours on that, but I better not. So that's the first test. We have got it now up to 55 bar. It's aimed to go up to 500 bar. So these are high pressures deliberately, but we are getting there slowly. This is why I don't have that good news for you that I hoped to have today. These are what are called pass-throughs at the top of the valve actuation systems, and they're for putting in electrical current, supposed to be sealed, and that's oil coming through these. And they're made out of Macor, which is an abomination of a material that I will never use again. I will replace it with a more suitable material in due course. So, in my opinion, with very credible assumptions, if you plug in what's possible with WinTP into NSTOR Sim, I think it can account for a saving of more than £1 per megawatt hour. And I hear you say, so what? £1 per megawatt hour is not very much, arguably. It's not much compared to the cost of a megawatt hour, but I'll come back to that point. And interestingly, the savings increase as the cost of wind goes up. And the Royal Society report was actually 2023. It was September the 8th, 2023 was when it was released. On the very day that it was released formally, it was the same day that there were 0 bids for offshore wind in auction round 5. And it was the first kind of tangible indicator that maybe the continuous downward trend of costs wasn't quite as rosy as we thought. So here's Jim's last remark. If that 1 megawatt hour saving was real, and if we consumed 1,000 terawatt hours per year, which I think is perfectly credible, then that would be indeed £1 billion a year for the UK. And that, so in proportional terms, it's small, but in absolute terms, because we spend so much on energy, it's not small. And this is a kind of a deliberately provocative question at the end. If it was as good as that, surely DESNZ would already be looking into it seriously. I could spend a month talking about that. So my concluding remarks, we do need a lot of hydrogen storage in the UK, no question about it. Medium duration storage of various sorts will do the heavy lifting. It's going to do the heavy lifting of future net zero UK. Standalone solutions like compressed air will give us a order of magnitude 5% reduction relative to just using hydrogen and batteries, which is the kind of default mentality of government at the moment. And if you put this in, you're talking about 0.6% better than that, which to a politician sounds tremendously unexciting, but it's still £1 billion a year. And then WinTP is an attractive form of wind integrated storage that you can implement anywhere, and et cetera, et cetera. This is the UK Energy Storage Conference, and today is the last day for submission of abstracts. Anyway, that's my final slide. This is a quote from a guy I don't like very much, but I like the quote, Mark Cuban. If you're looking for the next big thing and you're looking in the same place where everyone else is, you're looking at the place.
Thanks very much, Seamus. I'm going to abuse my position by making a comment. Which is that the people who've done the modelling, which BESNES used, which comes, it's first NESO, the National Energy Systems Operator, their modelling for the Committee on Climate Change, and modelling for the National Infrastructure Commission. They all looked at single separate years. So they simply can't see this very long-term need. You can't see this thing where you had a red ring in 37 years. Secondly, they set the level in the store, and we've checked this now explicitly with the two companies that did the modeling, equal at the beginning and the end of the year. Now, that is, as Seamus has pointed out, you don't have to do that. You can have them different and charge for it. But that's what they did, and it's what we did. But we did 37 years, and over 37 years, as the number of years
It
gets
doesn't make much
longer,
difference.
the error in doing that goes to zero. So we're okay. But if you do it with 1 year, it's not just that you don't see the long-term need, you grossly overestimate the need for other flexible supply, which is why the Committee on Climate Change, DESNES, the National Infrastructure Commission think we're going to need lots of gas plus CCS. And the reason's very simple. If the level of energy in your stores at the beginning of is the same on the 31st of December as it was on the 1st of January, anything you take out of store, you've got to put back by the end of the year. Anything you put in, you've got to take out. So you're actually only storing for 2 or 3 months. So with that boundary condition that you can't import or export energy from other years, you actually only store a very small amount of energy. So you're constraining storage to play a very small role, but you still have to meet demand. So therefore, something else must meet it. And that's why they have lots of gas plus CCS. Now, when we went to the Committee on Climate Change and said, why did you only look at 1 year? They said 2 things. First of all, they said, it's all right, we looked at some low wind years. But then it's worse, because in a low wind year, you'll need lots of extra wind. You'll be paying through the nose of it in average and high wind years when it's not used. And then we asked, well, why? They then said, well, we didn't know how to look at long periods. And I now know why this is. Those guys all assume perfect foresight. Whereas thanks to Stan Zachary, as Seamus has very clearly explained, their algorithm, first of all, that's wrong. We'll never have perfect foresight. We'll have pretty good foresight for up to a fortnight, maybe, for supply and demand, but never have perfect foresight, let alone for 37 years. But the trouble is, if you do it anyway, even though it's wrong, you have to look at the 324,000 hours at once. And then you have to iterate. It's very hard to look at. The amount of computing power, if you assume perfect foresight, goes up, I don't know what, something like exponentially with the period you look at. So the statement, we didn't know how to do it, I now understand. They didn't know how to do it. So they didn't do it. And it's just wrong. We're trying to get this over to them. And we've got it over to some of the consultants. And, the people in DESNES nod their heads, but nothing happens.